Good afternoon. My name is Jéssica Bersch, and today I'm going to present the study entitled How to Protect Our Facade Coating Mortars, a glance at different approaches to improve surface protection, developed by me together with my PhD supervisors. Building facades represent symbolic and architectural expressions within the built environment. Therefore, they are part of the community sense and well-being. These facades contribute to building performance and durability, namely by providing protection, for example, against water ingress. However, the facades are constantly exposed to air and rain. They are also prone to soiling due to biological and non-biological deposits. If the materials of these facades suffer degradation, their properties may change, such as porosity, surface texture, and microstructure. When we have mortar renders as coating for these facades, these renders influence degradation patterns and service life. And that is why it's so important to think about preventive treatments. Among the most noteworthy treatments we may have are photocatalytic, hydrophobic, and oleophobic coatings. Photocatalytic coatings normally include titanium dioxide in their composition. And by combining chemical reactions with superhydrophilicity, they may provide self-cleaning and depolluting effects to facades, further reducing biological growth. Hydrophobic coatings are normally composed of silanes or siloxanes, and they prevent the ingress of water and harmful ions. Oleophobic coatings offer a barrier that provides resistance against graffiti vandalism. However, few studies develop comparative assessments between these different types of protective treatments. So, this research investigates 13 surface finishes for lime-based mortars. Our objective was to identify which mechanisms offer the best overall protection for facades and identify limitations to be explored in future studies. Regarding materials, we have studied two different types of natural hydraulic lime-based mortars. The first one is a monolayer render and was applied with different types of paints. The first type of paint is a lime-based photocatalytic paint applied without and with an additional protective extra coating. Then we studied two silicate paints, both of which were applied with the photocatalytic coating 1, which is a commercial product recommended to be applied over the paint, and silicate paint 2 was also tested with photocatalytic coating 2 that could be applied directly to the mortar. Mortar 2 is a two-layer system, and the outermost layer was considered as a finishing render. That is why it was studied uncoated as a reference, and with the application of two different types of hydrophobic coatings, a hydrophobic and oleophobic coating, with photocatalytic coating 2, and with a sacrificial anti-graffiti coating. Two specimens were tested for each combination and were coated according to the manufacturer's guidelines, normally with the coatings applied in two layers. The methodological framework consisted of a series of surface tests. We measured gloss, color coordinates, static water contact angle, and roughness. We have also studied self-cleaning and anti-graffiti performance. All the results that are discussed were evaluated with analysis of variance and Tucky tests. For self-cleaning performance, we applied 5 stains of a methylene blue aqueous solution on each specimen. Then, the specimens were exposed to 145 hours of UV light. Color changes of the stained specimens were monitored throughout time and compared using CLab colored space. For anti-graffiti performance, we applied a silver spray paint over the specimens. Then, removal was attempted with a low-pressure water steam jet in 2 rounds of 12 passes. The cleaning performance was classified according to an existing scale from complete removal to no cleaning. Surface gloss can be measured using different geometries. In this study, for the three geometries studied, all the surfaces were classified as matte because they presented less than 10 glass units. Regarding the different geometries, 20 degrees, which is the lightest purple curve, showed mostly the influence of the mortar substrates, with M1 presenting around 1.5 glass units and M2 configurations 1 glass unit. 85 degrees pointed to the influence of roughness. Roughness results will be presented later, but what we identified was that rougher surfaces connected with lower gloss. Although 85 degrees is the geometry recommended for low gloss surfaces, in this case, as I mentioned, it captures surface roughness instead of coating types. 60 degrees was the best geometry to actually compare the protective coatings. What we have seen was that the hydrophobic coatings conducted to the lowest gloss values, while the anti-graffiti and photocatalytic 2 coating applied to the silicate paint led to the highest values. Almost all coatings applied over mortar type 2 reduced the gloss values of the reference samples. Normally, photocatalytic coatings resulted in intermediate values. These are the color coordinates of the different surfaces studied in their original form. What we have observed is that the color differences introduced by the protective coatings compared to the original mortar substrate or the silicate paint, for example, they generally supported good aesthetic compatibility. This means that the hydrophobic coatings or the photocatalytic ones, for instance, they do not induce great color changes compared with what was there before. What we can see is that L values dominated across all specimens. This is because we have a wide appearance, particularly in M1 with mineral paints, which is expected since lime-based paints and silicate paints were white. In mortar 2, the anti-graffiti coating and the hydrophobic one, they showed the least white surfaces, that is, with the lowest L values. Here, we can see water contact angle results, which are related to surface wettability. We consider 90 degrees as a threshold between hydrophilic and hydrophobic surfaces, being those with results higher than 90 considered hydrophobic. Firstly, if we look to mortar 2, we can see that the application of a hydrophobic and oleophobic coating or an anti-graffiti coating generated minimal influence on surface wettability compared with the reference specimen's uncoated mortar. Now, looking to the photocatalytic surfaces, what we can see is that except for the lime-based photocatalytic paint applied on mortar 1, all the other photocatalytic surfaces were hydrophilic, even with this test carried out without previous exposure to UV light. For surface roughness, if we look to mortar type 1, what we can see is that in the systems applied with silicate paint 2, we obtained the higher variability between the measurements. And this was because silicate paint 2 was applied with a lower thickness than the lime-based photocatalytic paint and silicate paint 1. These two paints conducted to the smoothed surfaces in M1. For M2, we obtained a uniform roughness regardless of the coating type. This indicates that the mortar itself or the different types of paints, they were the main responsibles for surface roughness instead of the protective coatings. Comparing this with contact angles, we saw that roughness did not directly dictate surface wettability, which was, on the other hand, primarily influenced by the protective surface coatings. This table is related to self-cleaning performance, and it shows color variations for all the studied systems throughout UV light exposure time. These color variations, they compare color coordinates obtained at different time steps with those obtained just after staining. If we consider 145-hour results, we see that the line-based photocatalytic paint conducted to the highest performance, the highest degradation of the dye, followed by the photocatalytic 1 aqueous solution. On the surface of the line-based photocatalytic coating, around 10% of the weight corresponding to the titanium element. In addition to that, we observed that some color variation was also obtained with other types of coatings, not only the photocatalytic ones, in lower extents, of course, but this could be related to their composition. For anti-graffiti assessment, none of the studied systems reached the best performance possible, which would be 100% removal of the spray paint. The best performing configuration was mortar 2 applied with the sacrificial anti-graffiti product. Here I show pictures of the 2 specimens tested before and after cleaning with the low pressure water steam jet. These specimens were classified with a class CN3 that represents visible residues with 30 to 85% efficiency. Since the anti-graffiti is a sacrificial product, its removal is expected to affect other surface properties such as gloss, and it should be reapplied after cleaning. Regarding the other systems, only mortar 1 and 2 applied with the photocatalytic coating 2 and mortar 2 with the hydrophobic and oleophobic coating showed a CN4. It represents that their surface was slightly affected by the cleaning process with an efficiency lower than 30%. They are also illustrated with images. All the other coatings get a CN5 class, that is, they did not present effective cleaning. From all of these results, we can conclude that there is a complexity to select optimal facade protection. For example, we could emphasize that although line-based photocatalytic paint led to the best performance for self-cleaning, some non-photocatalytic coatings also showed some dye degradation, probably due to chemical interactions that could be investigated. In general, photocatalytic and hydrophobic products were not effective in graffiti removal except for the sacrificial anti-graffiti coating. So we need to find a balance, and maybe context-specific degradation risks must be considered. For example, anti-graffiti coatings may be ideal for vulnerable low-level walls, while photocatalysts can be advantageous in polluted environments if they also ensure water resistance. Some ideas for our future research are to study different staining agents and water exposure, for example, investigate how rain and runoff affect soiling and cleaning, also carry out long-term aging studies, and it would be very interesting to have a complete facade system application where we could investigate the impact of constructive details, different heights, and orientations. I would like to thank the Portuguese Foundation for Science and Technology for the funding for this study, and thank you very much for your attention.